Okay, I think our session is about to start. So before we start, I would like to remind everyone, so this is a session that's in a hybrid mode. So we have online attendees and also in-person attendees in Shanghai. So that, yeah, there will be, in case that you have any question, you can ask either online or through the in-person session. And also I would like to remind everyone that the session is currently being recorded. And for every speaker, we will have 10 minutes for the live talk and 5 minutes of the Q&A, and we'll try to control the time and probably give some time check during the talk. And so we have 4 talks today, and I think, yeah, maybe let's get started. So yeah, I'm Chen Liu. I'm currently an offensive security researcher in Intel, and I had the honor to be the session chair of this session together with Professor Wendy Chong. So today we have our 4 speakers, and our first speaker is Dr. Wendy Chong. Dr. Wendy Chong is currently a distinguished professor in Hunan University, China, through the prestigious National Recruitment Program, and the Chief Scientific Advisor on Embedded Systems in Huawei Technologies. His research covers all aspects of real-time, embedded, and cyber physics systems. He is the Secretary-Treasurer of ACM SIGBEC and an executive committee member of ACM SIGDA, both by election. He chairs the ACM SIGBEC Best PhD Dissertation Award Committee. He chairs the automotive system track of DAC and founded the industry track of RTAS. He has served in the Best Paper Award Committee several times in RTSS, Euromicro DSD, CODES+ISSS cases, etc. As a chair of the member, his paper has received the Best Paper nomination in EMSoft, CODES+ISSS dates, and other conferences. He used to hold a permanent faculty position in the University of York, the UK. He obtained a PhD degree from the Technical University of Munich, Germany, and won the Best Dissertation Award. His bachelor degree is from Nanyang Technology University, Singapore. So Dr. Chang, stage is yours.
Thank you very much for the introduction. Ladies and gentlemen, this is Wanli. So I see Aviral, Al Farouk, Petru for America, and it's very early in Europe. And thank everyone for coming. The paper I'm presenting today is FLAM-PUF, a response attack-based, lightweight, anti-machine learning attack PUF. This is a joint in Hunan University, Chinese University of Hong Kong, New York University, Institute of Technology, Northeastern University of the US, and Huawei Technologies. Here is the outline. First of all, the motivation, followed by the method, performance, and eventually the conclusion. If you want security at a certain level, then usually you have to go low. If you want security at the application level, then usually you have to go down the systems. And if you want to have security in the OS kernel, then most likely you have to go down to the chips. This actually motivates hardware security being increasingly and developed in academia and industry, as it is considered to be the root of trust for the entire computing systems. That is physical, unclonable functions. They are a major hardware security primitives to be used for key storing in device authentication and identity recognition. So these PUFs utilize chip inherent process variations to generate input mapping relationships. And these relationships are known as challenge response CRPs. These variations are unique, hard to predict or reproduce, and hard to clone. Strong PUFs have a huge space of CRPs. However, even the strong PUFs, they are vulnerable to modeling attacks with the development of machine learning. So researchers have developed different kinds of strong PUF combination, as well as nonlinear sequential circuit correct learning. However, there are two existing problems for them. So these PUFs are either too complex, taking a lot of hardware resources, or they can still be successfully if they are not complex enough. So essentially, the learning, they can train a model to mimic the behavior of the PUF. Therefore, our goal over here is to develop a PUF with low hardware overhead and high resistance to modeling attacks. Here is the architecture of our PUF. It consists of regular A PUF, arbiter PUF, LFSR, linear feedback register, and a buffer. So during the initialization phase, first of all, the original challenge C is loaded into LFSR as its initial state. And then in each cycle, the N registers in LFSR generate an N-bit output as a direct challenge of A PUF. And then A PUF generates a direct response and transmits it to LFSR for configuration, updating, and cache buffer. So a first confusion. After repeating step 2 and 3 for n times, the buffer has collected an n-1 response and then feeds them back to LFSR as the feedback coefficient for the second confusion. So total 2 times of confusion. And now that the initialization is completed, we can start the real response generation. So LFSR repeats the same operation of step 2 and generates a new direct challenge. The FLAM-PUF generates the final response from A PUF, which can be n bits. We have evaluated our FLAM-PUF comprehensively from 3 perspectives. The first perspective, uniformity, uniqueness, and reliability. Uniformity indicates how the response bits are generated from the same PUF, same chip. Because there are only 2 possibilities, 0 and 1, so the ideal value would be 50%, which is the most difficult to model bit. And then uniqueness describes how different the response bits are generated from the same PUF implemented on different chips. And then similarly, the ideal value for uniqueness is also 50%. And reliability describes our performance and varying environmental parameters. So as can be seen, our FLAM-PUF is very close to the best PUFs in literature under these 3 metrics. We test our FLAM-PUF and 4 mainstream machine learning attacking algorithms, SVLR, CMAES, and deep neural nets. So we use a set of 10 to the power of 6 CRPs. So we can see the prediction accuracy is around 50%, meaning the machine learning attacks, they are not able to model or predict our input-output relationships, that is the CRPs, from our FLAM-PUF. And at last, the hardware cost. From our experimental results, we have achieved at least a 62% in gate equivalence compared to these state-of-the-art PUFs. Right, so Contributions. So as I have mentioned, the existing works all have tried to develop complex architectures to improve security, to counteract the machine learning. Essentially, they are trading space for security, and this is the first solution that trades for security. So it only consists of regular APUF, LFSR, and some basic logic gates. Fusion of space and time and can boost the system complexity, enhance the resistance to modeling attacks with machine learning. So as you can see in the PUF session, there are 3 papers on PUF. So probably is no for me to make some comments on the other 2 PUF papers as well, just to provide guidance for the audience. So if you look at the second paper, right, Cascaded PUF, so obviously they are following this direction as well, meaning complex architecture to improve security. And if you look at the third paper, so it's configurable poisoning PUF. Essentially, they use a pseudo random number generator. So the architecture is not that complex. So there are 2 APUFs and a random number generator. They're tested and the DNA. So not every mainstream attacking algorithm, and also is questionable because if you only have 2 APUFs combined together, maybe use a split modeling attacks, meaning they can develop a training model for APUF, 2 APUFs. This work is not hard, so the performance is a little bit questionable. But that said, these 2 are both great works, improving or advancing the state of the art. But I also just want to make some comments on their limitations. We also have our own limitation. Every work has its limitation. So is our solution requires cycles initialization to generate an n-bit response. And this is also the first work in trading time for security and space. However, from system level, most applications, if not all, actually all the applications we have observed, even the most critical real-time applications, they're insensitive to the nanosecond scale delay. With this, I'd like to wrap up the presentation. Thank you very much, and questions, comments, please.
Thanks a lot, Professor Chang, for the nice talk. And so, yeah, so feel free to start asking any question online or in person. So maybe let me get started to ask a question. So Professor Chang, regarding the performance impact of the proposed technology, is there any comparison with the previous work?
Thank you for the question. Yes, for performance, there are, as talk, there are 4 main mainstream modeling algorithms from. So we have tested all of them based on and algorithms, and because ideally the prediction accuracy should be 50%. It means the attackers are not able to model or predict this relationship. So from this table we can see in all 4 cases, either 64-bit or 128-bit. Are very close to 50%, but for the other like in literature, they are also around 50%. So our performance is similar to these parts. They are satisfactory. So our main advantage is to save hardware costs. Yes.
So is there any like the from delay perspective? Is there any what are the additional delay introduced with the proposed design?
Very good question. Thank you. So this is exactly the limitation. So we are So we always have to pay some price, right? So we want to keep the security performance, we want to keep the uniformity, uniqueness, reliability, everything. The other people actually, they have space for this, right? So they use complex architectures, taking a lot of hardware resources. We try to save hardware resources, but we also have to pay a price. So this is exactly the timing. So we need an initialization phase, meaning we need n cycles to configure the LLSR. So it's a double confusion phase. So only after these n cycles, is 64-bit, then 64 cycles, if 128 bits, 24 cycles, we can generate the real response, which is used for 122 bits as well. So this is the price we pay, meaning we are at the time delay. However, I also want to point out, although this is the price we have to pay, but because if you think about cycles, clock cycles is usually in the nanosecond scale, and from the application level, from the application perspective, because I mainly work on real-time systems, you can think about all possible, even the most critical, time-critical applications. I mean, they are not sensitive to the second time delay. So essentially, price, but is not visible from the application layer. Yeah, thank you for the question.
Yeah, thanks a lot, Professor Chang. Okay, yeah, thanks Professor Chang for the talk. I think well, let's transition to our next speaker. So our next speaker is Hassan Nassar. Hassan Nassar joined the chair of embedded systems in March 2020 as a research assistant. He received his bachelor degree with highest honors from the German University in Cairo, Egypt in 2016, and his master's degree from our University, Germany in 2019. So I think Hassan will deliver the talk online. So yeah, Hassan, the stage is yours.
Hello.
Hi, yeah, we can see you and we can see your slides.
Okay, great. So hello, I'm Hassan Nassar, and I will be presenting our paper, CaPUF, Cascaded PUF Structure for Machine Learning Resiliency, on behalf of my co-authors, Lars, Bauer, and Joerg Henkel. So let's start with the introduction. What are PUFs? What are physical unclonable functions? They are a lightweight alternative for cryptographic modules. And in the figure, you can see the orbiter PUF, which is the first ever design of a physical unclonable function. It consists of simple switches leading to an orbiter. And if the delay of the upper path is shorter, then the orbiter will output a bit of 1, otherwise it will output a 0. And the delay difference of the paths in the switches is dependent on the fabrication process of the ICs. So for one IC, it can have a shorter path for the upper one, and for the other, it can have it shorter for the lower one. And this cannot be known before fabricating and testing the IC. That's why it is unclonable, and it can serve as a DNA-like identity of the hardware. But how exactly does it work? So normally a PUF has an input which is called a challenge and outputs a response. And so, for example, going back to the figure from the slide, here the challenge is 0010, and only the bit that is controlling switch 2 is 1, so the switching is done. And hence, with each challenge, a unique combination of switching between the switches happen, and for each of them, the delay will be different, and for each of them, the response will be unique. So with each challenge, we will have a unique response. And now to evaluate PUFs, 3 main metrics are used. The first is reliability, which is the stability of the response under different environment conditions. So for example, with more noise in the system and so on, and the reliability ideally should be at 100%. Second is uniqueness, which is the interchip Hamming distance, which ideally has to be at 50% to be really governed by the fabrication process and not, for example, the routing on the chip. And finally is uniformity, which is the Hamming weight of the response. It also should be ideally at 50%, so the response is not biased toward a certain output type. Now we come to the main thread that we tackle in this work, which is the machine learning modeling attacks against PUFs. Let's say we design the perfect PUF with ideal uniformity, uniqueness, and reliability. And while it is unclonable, it can be predictable. To better understand this, let's consider an attacker that eavesdrops on the challenges sent to the PUF and the responses collected from the PUF, or even has control over the PUF for some time and can send it challenges and collect responses. And just for the sake of the simplicity, we consider this small arbiter PUF with 4 stages, so with an input response of 4 bits. The attacker will first eavesdrop on the challenge of 0000 and 0001, and for both cases, the attacker finds out that the output is 0. Then they can infer that the delay of switch 3, whether it is crossed or not, doesn't really affect the output, because in both cases it is 0. Then the attacker also eavesdrop on the challenge response pair of 0011 and find that the output now is at 1. Now the attacker can infer that switch 2 has a significant difference in the delay, and hence they can also infer that for challenge 0010, the response will be 1. They don't need to collect it, they can really find it out based on these only 3 observations. Of course, this is just a motivational example with a very short chain. Bigger PUFs will be more complicated. For example, if we have 256 switches, it will be more complicated. However, machine learning can actually break this security and can model the PUF. And in the literature, it has already been shown that SVM and logistic regression both can break PUFs with sufficient challenge response pairs. So to combat such predictability, solutions have already been suggested, and they can be seen in 2 categories. First, having architectural modifications, for example, XORing the output from several PUFs. However, this is a little bit, has a low overhead. However, it is not fully secure, as for example, for this XOR, it can be easily modeled as an addition by machine learning and will get easily broken. The other alternative is using cryptography. By hashing or encrypting the output response, it will be as secure as the output of a crypto module. However, this comes with a huge latency and area overhead. And this is where our solution comes. We want to build a lightweight machine learning resilient PUF. So to have it not with a high latency or high area overhead, but also to have it resilient to the attacks. And to do this, we use the PL-PUF from the literature as a basic block for our bigger cascaded PUF, because it has lightweight characteristics. So what is a PL-PUF? It is generally the same design as an LFSR. However, instead of using registers, we use a mux and inverter as the building block of the design. By doing this, it converts from a sequential circuit to a combinational one. Also, by having this, it is very lightweight because each element in the chain can be initialized by 1 bit of the challenge and will output 1 response bit. This means that we only need 2 gates for 1 response bit, which is very lightweight. And also it has another dimension of unpredictability that we harness, which is the responses are collected into flip-flops. and the frequency used for collecting the responses really affect the response. So if we use, for example, a 50 megahertz clock, the response will be different than if we use a 100 megahertz clock. And using this PL-PUF, we build CaPUF as a 4x4 grid using 16 PL-PUFs arranged in rows and columns. And we use two factors to have the security and lower the predictability. The first, the output from one PL-PUF in the chain is the input for the next one. And therefore, when we reach the final stage, the output comes from a challenge that is derived from other puffs and not the exact challenge that was applied to the puff itself. So it is not, it has no direct relation to the previous, to the main challenge. The other thing is, as I said, we harness this frequency control. So by having these frequency controllers, they have as an input also part of the response from a previous puff. And based on this, we have either the initial frequency or half of it or 1/4 or 1/8 of it. And by this, with each new challenge, we have somehow internal change in the puff itself. So as if the output come from an exactly new different puff with each new challenge. And in our paper, we have a mathematical model for how this increases the security, how this make it more complex to model the puff. But unfortunately, for time limits, we have to skip it. We also designed our puff as having 4 stages, 1 input stage and 2 intermediate stages and an output stage. And this is to be able to mitigate attacks where the attacker tries to use the knowledge about the internal structure from the puff to actually fine-tune the model. We also have to skip the details for the time limits. And now that we have discussed the design of CaPUF, we go to the details of the implemented system for performance and results. So we used 4 different VC707 boards to implement our system. So to have a challenge generator and put the challenges to the puff and collect the responses, and then analyze them on a PC and run to attacks. And we have 65,000 random challenges, and we use 50,000 challenge response pairs for the training, and the rest to test whether the puff will be broken or not. Starting with the first results, which is the quality metrics, we can find that they are all in the ideal range, and also they have the expected statistical distribution, which means that the puff itself works well. However, the more important result is the predictability, where the machine learning models able to accurately predict our CaPUF or not. And for this, our CaPUF was as good, the prediction was as good as flipping a coin. So it didn't go higher than 50%, and it didn't have any rise even with using more CRPs. And this means that the attacks were not able to break our puff. So now to conclude, the idea of CaPUF is to use 2 factors to achieve the machine learning resiliency. First is to cascade the inputs and outputs of several lightweight puffs. And the second is controlling the frequency of each lightweight puff based on the response from the other puffs. And our experiments show that CaPUF is resilient against machine learning attacks. And for more information, our paper contains the mathematical model that explains this enhanced security. And now I thank you very much for attending our presentation. And if you have questions, I would be happy to answer them.
Thanks a lot, Hassan. And I think we have time for maybe one question.
Yeah.
Any question from online audience or in-person attendees? Please feel free to ask. Okay, yeah, if there's no questions, in the interest of time, let's thanks Hassan again for giving this nice talk. So yes, our co-host, Professor Chang, will introduce the next two speakers.
Okay, thank you. The next presentation is given by Chia-Chih. Their work is enhancing reliability and security configurable poisoning PUF against the modeling attacks. Chia-Chih received the master degree from the Graduate Institute of Communication Engineering, National Taiwan University, Taiwan in 2016. He is currently pursuing his PhD degree with the Graduate Institute of Electronic Engineering, National Taiwan University, Taiwan. His current research interests include silicon physically unclonable function machine learning-based modeling attacks and hardware security. Okay, it's your turn, and Chia-Chih.
Okay, thank you. Can you hear me?
Yeah.
Oh, okay. So I will share my screen. Okay. So, okay, good afternoon, everyone. We are glad to present our work enhancing the reliability and security of configurable poisoning PUF against modeling attacks. So, physically unclonable function or PUF ensures is a hardware-based solution that exploits intrinsic physical characteristics to provide digital fingerprints. In device authentication, strong PUF has widely used due to its exponentially large challenge response pairs. Ideally, PUFs are supposed to be unclonable and unpredictable, but however, most of the PUFs are in fact learnable by machine learning algorithms. An adversary can train a PUF model to impersonate the device by collecting a small subset of CRPs. So among existing countermeasures, we think the adversarial-based PUF is an efficient solution because it is based on the inherently hard learning problem. The adversarial-based PUFs consist of a conventional learnable PUF, typically an APIPUF, APUF, and a state function to invert a subset of internal APUF's output. When the state transition mechanism triggered, some of the learnable PUF's output are inverted in the change response space. So the poison the data will make the machine learning algorithms struggle between two distinct objective functions in the training process. So therefore, the state transition mechanism is critical for adversarial-based PUFs. Previous works either takes challenge as the input of state function or randomly choose a predefined state. A challenge-dependent state allows the verifier to control the reliability of the internal APUF, but it also leaves potential risk for an attacker to prompt the state transition. On the other hand, a challenge-independent function randomly switches the state to provide a security guarantee. Nonetheless, the response becomes unreliable in noisy environments. So therefore, we would like to explore a win-win solution for security and reliability by introducing another learnable PUF to the internal state. The proposed configurable poisoning PUF or CaPUF in short works as follows. A shorter random number generator on the device first generates parts of the challenge CD and send it to the server. And the server then sends the rest of the challenge bits, say CS, back to the PUF. And CD mitigate external control from an attacker, and the CS remains the configurable reliability for the verifier. The complete challenge matrix C concatenated by CD and CS is then applied to two PUFs. APUF 1's response are served as a secret key and dot product with the challenge matrix C. The result is the internal state of the CaPUF. And afterward, the internal state inverts a subset of APUF 2's responses. And finally, a circular shifting is applied to prevent a biased CD. The construction C dot R1 XOR R2 establishes a reliability trapdoor which makes the adversary hard to obtain reliable responses. We demonstrate an example for n equals to 5. Suppose the R1 and R2 are generated given the challenge matrix C. The response R1 will select a subset of columns in each row of C and XOR them with R2 to get the final response R. If an error bit occurred in R1, the noise will be propagated to all other final response bits via the dot product. The result is a large Hamming distance between two responses. This implies that randomly querying the CaPUF will obtain noisy responses. In addition, our CaPUF can be mapped to a computationally hard problem, the learning parity with noise problem. In an LPM problem, the goal for an attacker is to find the secret vector S given the result of the noisy linear equation B and the coefficient matrix A. The LPM problem is a well-known hard problem studied in cryptography and coding theory. In the CaPUF, that C be the coefficient matrix A, that R1 be the secret vector S, and R2 be the noise vector E. Then solving the CaPUF is at least as hard as solving an LPM problem with a secret length of K and the noise rate of 50%. So to solve this LPM problem, the time complexity is big O2 to the K. So we summarize the property of the CaPUF as follows. First, the CaPUFs establish a reliability trapdoor based on information asymmetry between the verifier and attacker. The verifier can obtain reliable CRPs by configuring part of the challenge CS. The poisoning attack for CaPUF is twofold. One is the inversion of R2's responses, and the other one is the noise amplification introduced by the dot product. And finally, the proposed construction is provably secure. Although server can control the reliability of the CaPUF, the environmental noise still cannot be totally eliminated. When the environment becomes very noisy, the reliability of the CaPUF degrades dramatically. Therefore, we propose an error correction on the verifier side to reduce the false rejection rate. For example, if a received response does not match the server predicted one, then the server will try to recover it. A brute force search for finding possible error bits is applied to correct the error. To investigate the reliability of the CaPUF, we conduct an experiment under different noise level. APUF with random challenge applied in the color blue is set as a reference to reflect different noise levels. Figure A shows that the reliability of CaPUF using either random or reliable challenges. We can observe that the reliability decreases dramatically even if the noise rate is increased incrementally. This shows that the response will become noisy when an adversary randomly queries the CaPUF. We then compare the reliability of the CaPUF to other puffs and show in the figure B, as shown in figure B. The result shows that the CaPUF is much more resilient to environmental noise. We also analyze the reliability and theoretical security compared to adversarial puffs. The result of our construction include in both directions. We then investigate the efficiency and security of the error correction mechanism in terms of the false rejection rate and false acceptance rate. And figure A shows that the correcting 1 or 2 error bits on the server side is sufficient to significantly increase the authentication pass rate. On the other hand, figure B shows that the error correction does not significantly increase the authentication pass rate under random guessing. Finally, we show the performance of the empirical deep learning attacks. The prediction accuracy should be 50% in ideal case. We evaluate the AA-PUF, which is adversarial A-PUF, the state-of-the-art challenge-dependent adversarial PUF with random and selected challenges. The result shows that the AA-PUF is susceptible to external control. When the challenges are properly selected, the AA-PUF becomes learnable. On the other hand, since the adversary cannot control part of the challenges, the CaPUF is resilient to deep learning attacks. So this is our conclusion that we present a novel adversarial-based PUF, CaPUF, that takes a batch of challenges as input to generate responses. The proposed construction provide a theoretical secure promise based on the LPM problem. And the third one is the reliability trapdoor of the CaPUF allows verifier to maintain the reliability under noisy environments. And the last one is an error correction on the server side can further reduce the false rejection rate without additional cost on the device. And this is our reference, and thanks for your listening.
Okay.
Okay.
Thanks for your presentation. Is there any questions from both online or on-site? No. Okay. Maybe I have a question.
Okay, please.
If from your slides, I didn't see how the experiment is implemented. So I want to know whether your experiment is conducted by simulation or device-based experiment.
Oh, it's a good question. Our experiment is based on simulation because APUF is proof that it can be modeled as a Gaussian using Gaussian distribution to model the APUF. Yes. So we conduct a Python simulation to do our experiments. Okay, so and from the type of your work, it's configurable pointing. Okay, PUF against the modeling attack. So yes, how to okay how about the configurable work? I mean, is your configuration is frequently doing or not? And I mean, in practice, the configuration will take some overheads for real implementations. Okay. Yeah, our configurable is mainly for the reliability, and so if you meet a noisy environment, you should choose some reliable challenge. That means for APUF, it's a delay difference large one. So configurable in our design, it means that the reliability is configurable. So you can choose your challenges and to get a stable response. Okay. Okay. Is there any question? We still have time. Okay. If not, I have the final again another question. Yeah. How do you think the difficult to do your work in device based experiment? I'm sorry. Can you say that again? I mean, okay. I mean, your experiment is simulation based. Okay. So yes. I see. So I want to know: is there any difficult to do it in a real device? Oh, you mean the discrepancy between the practical implement or the simulation? Yeah. Oh, actually, because our PUF is the only physical characteristic is APUF, and it is widely studied. So I think it's the rest of the design are totally digital. So I think it's not that large discrepancy between the practical usage and the simulation. Okay. Okay. Yeah. So, thank you. Thank you. Okay. Thanks. Thanks you. Yeah. Okay. So we come to the last speaker of this. And the next work will be presented by Mohammed Abd Reham. Okay, their work is BLAST, banning the black hat high-level synthesis tool. Mohammed Abd Reham received his bachelor technical degree in computer engineering from Defense University Engineering College Ethiopia, and master tech degree from Defense Institute of Advanced Technology, Pune, India. His
He is currently pursuing the PhD study at the IIT Guwahati, India. His current research interests include the verification of high-level synthesis, hardware security, and embedded systems. Okay, it's your turn, Mohammed.
Can you hear me, sir?
Yeah, you can begin.
Okay, thank you. Thank you.
Yeah, you
okay.
begin. Okay.
Okay. Hello, everyone. My name is Muhammad Abdurrahman. I'm going to presenting a paper addressed within the black hole high-level synthesis. So this is my colleagues. So this is my presentation outline. So when it comes to the introduction, as you know, this high-level synthesis is the process of translating this abstract specification like can be C or C++ into RTL. Then it passes some processing stage. So finally, to generate data path and control path generation. So once we have synthesized this one using the bidirectional tools, we finally get RTL structure which contains control FSM and data path. So why we choose this high-level synthesis for our purpose? In this case, you know, instead of designing a component using Verilog or Verilog code, better to C or C++, because design at higher abstraction level means it is a shorter design cycle, and specification in C or C++, the complexity of a design, specification is simply at higher abstraction level, and it is easy to explore. So design space with high-level synthesis tools, and also to design accelerator instead of using this Verilog or Vivado, better to use this high-level specification like C or C++. Then the other one is this hardware trojans. Now this is a malicious modification of the design by the employee. Maybe it may leak some information, it may create some backdoor for attackers. Maybe it will change also functionality of the design, even it will halt the system down. So in a recent study in these papers, we have seen that these hardware trojans are actually being inserted by the high-level synthesis itself. So based on that, our motivation is simply, you know, this translation from C or C++ to RTL is not entirely secure. Most of the design also depend on the third party of intellectual properties. And our main, in this black hole, high-level synthesis in this paper, there are C attacks. The path regulation attack, degradation attack, and downgrade attack. Then our aim is why not we implement this one into the the Verilog code. Then we have also checked that no techniques that can detect this high-level synthesis hardware trojan. So based on this motivation, we developed for high-level synthesis hardware trojan detection. And also we show all these three hardware trojans can be identified by our method. And also we evaluate the framework on various benchmarks. So this is the overall flow of our detection mechanism. Assume we have the C or C++ code, then we use a bidirectional tool, then hardware trojan insertion is takes place in this one, then RTL code will be there. Then after that, we are going to extract this RTL XMD from the RTL. Actually, in this case also, we have one tool, fast sim tool, which will pass to do this one. Then once we have extract this RTL XMD from RTL, if there is some inconsistency, I will come on that in detail. Then if there is some inconsistency, we detect a path explosion attack may be there. Then once if it is consistent, then there is RTL XMD, and this one also we have consistency XMD. Then we are going to use equivalent tools, which will pass to find this DA attack and the DJ attack. So let us one by this is how we are going to construct XMD. Actually, in our equivalent checking, we have two conditions. For example, in this case, a trace of an XMD is a finite walk from the reset state key node to itself. As you can see, we have here one trace, we have here one trace. So to check these DA and DJ attacks, we are going to consider two conditions: condition of execution and data transformation. This condition of execution, CAPUF, a trace PUF, is a logical expression override which must satisfy by the initial data state in order to traverse PUF. The other one is a data transformation. From one state to other state, there will be some data transformation. Then we are going to consider this one. So to check this equivalence between these two traces, then we have to check whether this condition of execution of these two traces and data transformation of these two traces are equivalent or not. Then based on this one, first we have to find the trace, then we have to find this condition of execution and data transformation. Then we have to check whether they are equivalent. So as you can see after the FCMD examples, this one, basically as I have told you, there are two basic components in the RTL. There are control pattern in there, there are data passes here. So based on this control patterns, which operation is performed in each state, we can decide by using this data pass. So finally, we can construct here RTL FCMD. For example, as you can see here, this is some data passes. You know, this one is a control signal. Then based on this control signal, for example, this is we can assign some values. Then assume if this one is 1 in this register, we can add, we can store, and we can write from this one. If it is M1 is there, if it is 01, assume let us take this input. If it is 1, let us take this input. Then if it is this control pattern is 1, we can take it this maybe then subtraction. So based on this one, simply we see R1, this output will come into R1. Then after that, what is this one? What is this subtract? F out means this F out will be F left in, and this one, it will take it this one, it will take it this one. For this one also, we will take it based on this control assertion pattern. Then finally, we will get some FCMDs like this. Then based on that, we can construct FCMD in this way. We can construct RTL FCMD in this way. So let us see one by one how to detect this one. When you detect this battery exhaustion attack, you know, managing energy utilization is a key design principle in a circuit design. So battery exhaustion attack can simply drain out power by including some extra or idle functional units. So in RTL code, you know, there may be some idle functional unit. If there is no idle functional unit also, our tool can insert some functional units by first we have to identify which one is the critical path. Then without, if there is no critical path, we can add also some idle functional unit in that one. So these idle functional units are reused to execute some fake operations. Then no idle functional that will may insert. So the result of operation will not be stored by simply disabling the right operation. So this detection will be identified during FCMD/ from the RTL. So as you can see in this example, this one is the original. Assume this is the original data pass. We have multiplication operation R1 and 1 and 2. This one is the modified data pass to introduce these hardware trojans. As you can see here, there is a multiplexer in multiplexer here. There is original input is there. If this hardware trojan is active, then it will take this this value, not the original one. This one also if it's active, will take it this one. Then this value again negates. Then it will continue like that. So based on in that way, we can introduce these hardware trojans in our RTL code. Then we are going to find a way which will pass to detect this thing. So our algorithm is this one actually simple. First, we are going to find bit flip registers. Simply, we are going to buy, you know, in this case, bits are flipped. Every time bits are flipped. So we are going to find all bit flipped registers. Then we are going to find also collect all idle functional units. So for each bit flipped register and for each idle functional units, we are going to apply a rewrite method from the idle functional units. Then once we have do this rewrite method, if the input pattern of F5 contains any register from this bit flipped register, then we can say that there is a possibility of this battery exhaustion attack. Then by finding that one, we can say that there is a battery exhaustion attack. When you come to this degradation attack, downgrade attack, insert a few empty states or bubbles in the control FSL. This bubble creates a diverse in the control flow. So alternative trace consumes some extra flow cycle. For example, in this detection mechanism, simply we are going to use an equivalent checking tool. For example, as you can see, this one is CFCMD. Then after that, as you can see in this one, if there is hardware trojans, there is a diverse trace will be there, some additional state will be there. But as you can see in this example, the output is same. No difference on the output. Simply we are going to find what is this extra traces in this example. Then we are going to find that condition of execution from that one. Then we can find this one. So this alternative trace consumes some extra clock cycles before coming back to the original behaviors. So this may degrade the performance of our design. So simply I'm not going in detail this. See the equivalent checking algorithm. This one is the attacker detection mechanism. Simply we are going to find a trace. Actually, to find the trace, we use a clean to which allows to find each trace in both assemblies. Then we are going to select a trace from one of them. Then find test case for that trace. Also, we can use a clean for that one. Then by using data-driven approach, we are going to find a corresponding traces for the other FCMD, for example, Q1 for the M1. So then we are going to whether their condition of execution and data transformation is equivalent. If they are equivalent, actually there is no this attacks. But if there is, if this one is their condition of execution are not, if they have some common condition of execution, and if it is data transformation is equivalent for both these two traces, then we can say that there is a DA attack, otherwise there will be a DJ attack. So simply this is the algorithm. We have to check for each trace condition of execution, whether this one is a stronger condition than the initial trace for the CFCMD. And we have to check whether their output is correct. Because as I have told you, in the attack, the output should be same. Simply adding some extra traces, then simply increase the loop. It will simply degrade the operation. The other one is DJ attack. In the DJ attack, simply change the functionality of the input specification, reduce the number of executed round in secure hash algorithm. As you can see in this example, this is A and B1. This the sum operation will be there. Then the loop will continue until NB1 is until NB1 the value is into LB1. But we can make it like this. Simply to compromise the security of the algorithm, we are adding some additional constants. For example, in this example, NB2. This NB2 may be less than the value of NB1. Then if trigger condition is active, then it will take it NB2. Then the loop will be, for example, if this one is 64, if this one is 32, then if there is a trigger Trojan there, then it will be minimized. It will be, instead of executing your 64 times, it will go through 32 times. Like that, we can also demonstrate this DJ attack in the RTA. So as you can see here, I is the NB64, but if the Trojan is active, it will be 32. If it is not active, it will be 64. Then like that, NB value will be depend on the value of this hardware Trojan. So based on that, we can compromise the security of the algorithm. So as you can see, this is the DJ attack algorithm, which I'll pass to detect. So in this case, the output may be equivalent or may not be equivalent after inserting this hardware Trojans. For example, if it is TJ which is equal to 32, then as you can see, after unrolling this loop, this is unrolling for this example, unrolling this one. So it will be 64 times, but if it is 32, it will be 32 times will be there. So if you see the overall output, the output may not be different, will be different for these two traces. But if you take NB which is equal to 64, still the condition is there, it is not active actually. Then in this case also this output and this output will be also same. So we have to consider all these things together. Then finally we can actually our aim is to find these extra traces. Then in that traces we are going to find the condition of execution of each traces. Then based on that we have to compare this trace with the original C code. Then based on that we can say that this is the Trojans. So when we come to the experiment, actually, we have tested with various benchmarks, actually. We use a Viva HLS tool, 2019.2. Then we use also this clean to generate that one. Then we implement this one is Python. So we have used different instances. In this case, we had some 1 instance, 2 instances, 3 instances. Then detection time also not much. Then again, also we have checked actually area overhead also. It is minimally impacted actually, not much. Then also we have seen this some delays. Actually, this delay synthesis delay, it may not be actual delay. Then we have seen that also may not affect much after inserting this hardware Trojans. So when it comes to the conclusions, we present this blessed framework to detect high-level synthesis tools inside hardware Trojan with this RTL. We have shown that all 3 Trojans caused by this black hole high-level synthesis are detected by our framework. Overall detection time is reasonably similar actually. We have also analyzed area and delay rate for our benchmark. It is inclusion of hardware Trojans minimal impact the area and delay. The performance of less also this one. Actually, high-level synthesis optimization also considered in this one because high-level synthesis there are its own some optimization techniques. We have also considered this optimization techniques. What will happen after inserting these optimization techniques also. Then we have also tested this bias benchmarks. Thank you very much.
Okay, thanks, Mohammed. That's good work. Okay, but the time is up. So okay. If anybody have question, maybe we can have one QA. Okay, if not, okay. Thanks for all the presenters for this session. Okay, if you have any additional questions, you can contact the authors by email. Okay, so thanks for all the audience to attend this session. Okay, see you.
Thank you. Thank you.
Thank you. Yeah, and for the speakers and attendees, like please attend the post sessions. There will be many interesting post works showing a manner of post, and I think you can find we have attended that either in person or through the virtual platform. Thanks.